So moving on to the second step in this 4-step process that we are going to be thinking about for the use of glucose as a fuel. We just had a 30,000 foot view of glycolysis. Now we're going to talk about pyruvate dehydrogenase chemistry, just refreshing your brain. We've got the citric acid cycle that will come next, and then electron transport and oxidative phosphorylation. So let's consider what happens now with pyruvate dehydrogenase chemistry. So let's review sort of where we've been. Again, that's going to be the second step. Glycolysis was our first step. So let's zip back to our main 30,000 foot view sort of image here, and let's orient and fly in with where we're at, right? We just took glucose, went through glycolysis, and we ended up with pyruvate, okay? Now what we're going to talk about is pyruvate dehydrogenase chemistry. So a couple of important things to highlight here. We're crossing the lipid bilayer of the mitochondria. So we are now going to be having a mitochondrial process. Okay, this process is ultimately going to generate acetyl-CoA, and it does so by liberating one carbon atom as CO2. So we talked briefly before, but we'll highlight again, you don't get to do chemistry, and this is an oversimplification, but for our understanding right now, you don't get to do chemistry in the mitochondria unless you have oxygen available. So let's sort of map those details on with what we see with this picture here, right? We talked about taking glucose and going through and doing glycolysis. Let's just map on and remind ourselves that when we go in this direction, this is gluconeogenesis. Right? That's the reverse of glycolysis. It takes pyruvate derived from non-carbohydrate precursors, and it's going to synthesize it into glucose. Okay? But we're going to talk about what's on the right arm over here. Since we've dipped into the mitochondria with pyruvate dehydrogenase chemistry, it must mean we are in aerobic conditions. We've got oxygen around. Okay? So everything that I'm going to highlight in green here has to do with what we're talking about with pyruvate dehydrogenase chemistry. Okay, so we've dipped into the mitochondria, and reminding you what we just sort of indicated, we don't do chemistry in the mitochondria without ample oxygen supply. That's an oversimplification, but it's going to allow us to understand this process right now. So we're going to say the body will not allow entry without oxygen. Will not allow entry without oxygen. Okay, so let's take a look at what's happening here. So again, we've got pyruvate, okay, and what we're going to do, and we've got this color-coded here, we're going to see that we've got one carbon atom that's going to come off as carbon dioxide, and we're going to attach these other two carbons to CoA to generate acetyl-CoA. So that's sort of what's happening here. An important piece to highlight is this is an irreversible process. Oops, that doesn't look like an arrow. An irreversible process, okay? So this is irreversible. That will be something we'll see as a common theme with some reactions, particularly ones that generate CO2, is this is an irreversible process. But we generate acetyl-CoA. Remember, acetyl-CoA was one of those important branch point metabolites. We're going to see here, sort of leading into our next 30,000 foot view step, that's going to be the citric acid cycle that we're going to see here. But we're just sort of talking about this single step here with pyruvate dehydrogenase chemistry. But we generate acetyl-CoA. So let's go on now. We haven't written this down yet. Let's write what the net reaction is for pyruvate dehydrogenase chemistry. So it's going to take pyruvate. It's going to snip off one carbon atom and generate acetyl-CoA. That one carbon atom becomes CO2, and we squeeze that sponge a little bit, and we generate NADH. We generate a reduced cofactor. That is going to end up going on to the electron transport chain. We'll deal with that in our fourth step here. Okay, but here's the process that we have under aerobic conditions. So one of the things that we're going to highlight is, well, what happens if you're operating under anaerobic conditions? Now, we as humans are what we call an obligate aerobe. We require oxygen. We cannot live without oxygen for very long. But we've heard about things like anaerobic versus aerobic exercise. We know that our body can operate in that anaerobic space for short periods of time. And that's what we're going to see over sort of with this left arm over here. What happens when you are under anaerobic conditions, when you're without oxygen? Well, if you remember from our 30,000 foot view with glycolysis, and if you don't, I'm sort of going to give you some of the highlights. We ended that video talking about the importance of doing two things in order to have glycolysis continue. Glycolysis, again, being a rapid but inefficient mechanism to generate energy. Okay, what you have to do is you have to do something with pyruvate and you have to regenerate NAD+. Okay, so for glycolysis to continue, you have to do two things. You have to do something with pyruvate, and then you have to regenerate NAD+. Well, let's look back over at our pyruvate dehydrogenase chemistry and see if that sort of satisfied it. Well, we certainly did something with pyruvate because we converted it into acetyl-CoA. And if anything, it doesn't look like it regenerated NAD+. It actually looked like it used up some more NAD+. But keep in mind, and it's not inherently obvious from this picture, but what happens with all of this NADH that's generated, and once we've been given a ticket to go into the mitochondria, that means we also have permission for the electron transport chain to use all of those NADH molecules and deliver their electrons so that we can generate a proton gradient and synthesize ATP. So once we've dipped into the mitochondria, we have a fairly easy way to regenerate NAD+, because we're going to deliver that NADH to the electron transport chain. So even though it's not obvious, both of those things are happening on the right side here. But let's say that we're not allowed to enter into the mitochondria. Let's say that we are under anaerobic conditions. What are we going to do then? Okay, well, herein is this sort of alternative arm, and this is what we call homolactic fermentation. Okay, so this is called homolactic fermentation. And this is a really important piece when you consider anaerobic muscle activity. Okay, so what's going to happen here is you are going to incorporate an enzyme called lactate dehydrogenase. So LDH is lactate dehydrogenase. Okay, and what we're going to do is we are going to take pyruvate, see if you can look at these molecules. This is one of these skills that you need to know how to do. Look at molecules and compare their redox state. Okay, if we look at what's different in these molecules, we can see the difference is what's happening at this carbon atom. We've got a ketone in what we have with pyruvate, and then lactate has an alcohol. So going from pyruvate to lactate, we reduced that metabolite. That must mean it is coupled with an oxidation reaction. That oxidation reaction is going to be to take NADH and make it into NAD+. So the beauty of lactate dehydrogenase chemistry is it does both of these things. It handles the pyruvate production, gets rid of pyruvate by converting it to lactate, but it also regenerates NAD+ in the process. So it's sort of a 2-for-1, if you will. Lactate dehydrogenase chemistry is going to generate lactate and regenerate NAD+. Well, here is sort of part of the problem, though, is lactate is what we call a dead-end metabolite. And what do I mean by that? Well, there's not a lot we can do with lactate other than back out of that lactate sort of garage that we parked ourselves in, remake it into pyruvate. Well, if you want to do that, you're going to need to use NAD+ for that, okay? That process won't happen until you are under aerobic conditions. So we call this paying the oxygen debt. At some point, you are going to have to deal with the waste product that you made with lactate. And athletes know this, right? If you have strenuous muscle activity, anaerobic exercise for a lengthy period of time, and by lengthy, I mean probably like 5 minutes, you will accumulate lactate to the point where it is uncomfortable in your muscles, right? When we look at this process in detail next semester, we'll actually talk about what happens to actually deal with that lactate. Okay, but it is a short-term solution to allow for continued glycolysis for that rapid but inefficient production of energy. But at some point, you have to deal with the fact that I've been making this garbage just to allow this process to continue. I have to deal with that right now. And so you deal with it by reversing lactate dehydrogenase, remaking pyruvate, and allowing it to enter the mitochondria to be metabolized. Now, there's a lot more to those biochemical processes than that oversimplification, and we'll get into those in much more detail next semester. But this is sort of a good overview of sort of pyruvate dehydrogenase chemistry, but then introducing this concept of homolactic fermentation. One last little piece that I want to add in here, it has to do with the fact that when processes are irreversible, that allows certain things to happen and other things not to happen. Okay, so I hope you see that glucose can easily be converted into acetyl-CoA. When we consider fat metabolism, so when we consider, and let's actually put it as triglycerides. When we consider triglyceride metabolism, triglycerides can only be produced into acetyl-CoA. When we talk about fuels and their metabolism, every fuel can be made into acetyl-CoA. Only carbohydrates and some amino acids can be made into pyruvate. But if fats, and specifically the fatty acid component, can only be made into acetyl-CoA, right? And I just told you that once you get to acetyl-CoA, you cannot go backwards to pyruvate. So again, if we highlight this here, the ability to take acetyl-CoA and make it into pyruvate cannot happen. So this is a big fat no. So let's do this. This is a big no. That cannot happen. Pyruvate to acetyl-CoA by pyruvate dehydrogenase. That's the only way that that can happen in mammals. We cannot take acetyl-CoA to make it into pyruvate. And why that's important is if you want to make glucose, glucose is made from pyruvate by gluconeogenesis. So two things, that's a costly process and it requires pyruvate. So the fact that triglycerides can only be made into acetyl-CoA. Acetyl-CoA cannot be made into pyruvate. Pyruvate is what's necessary to make glucose. See if you can see this sort of double negative here. We cannot convert fats into glucose. So if you wanted to ask the question, can I take all of that adipose storage that I have? Can I take all of those triglycerides and make them into glucose? Again, a big fat no. Fats cannot be made into glucose. We will take a deeper dive on this next semester when we talk about how diets like the ketogenic diet work, how you maintain blood sugar when you are not consuming carbohydrates and you've tapped out your glycogen stores, which are gone after about 12 hours. So what you need to do is you need to take non-carbohydrate precursors that are generally derived from amino acids, from proteins. You use the proteins as the building blocks, but you use your triglycerides as the money. And that's one of the reasons why ketogenic diets can be so helpful in eliminating sort of adipose tissue, is you are using your adipose tissue to pay the cost of making the glucose that your body needs in its bloodstream, but you are not consuming in your diet. All right, so a nice little tie in there with how irreversible processes allow us to say that we cannot produce glucose from fats.